Okay, so good afternoon, everyone. This is the last session. I'll try to keep it as interesting as possible. And as we move along, maybe you can stop me if you have questions. What I'm going to talk about is intelligent connected mobility in the 5G era, or as I said, we are trying to touch upon the various use cases. In this presentation, I will only cover the mobility related use cases and maybe touch upon a broad overview of the other use cases that are possible in a 5G network. uh, the idea of this entire presentation of this session is to give you certain keywords, jargons, or kindle your thought process in the direction of building good use cases. I don't think we have enough time to go deep into any of the use case, but I hope if I'm able to trigger a thought process at the end of this presentation or the end of this session to think about the use cases that 5G can enable, I think it will be time well spent. Having said that, now if we look at the broad spectrum of things that are driving 5G, so it's basically driving a multi-trillion dollar economy with precision agriculture, construction, education, retail, smart manufacturing, mobile experiences. I mean, you name it, and the domain has a 5G use case in it. As I said, we are not going to touch upon every part of it, but some of the use cases that I have highlighted here, for example, in smart agriculture, we have precision farming or smart irrigation, where the sensors are used to monitor the soil and the crop, and then various things like smart irrigation, they get activated or controlled based on the measured parameters. The number of sensors, if done at scale, can run into millions. The number of control points can run into millions. So basically, this is a very high density kind of a use case that will get enabled. If we look at smart manufacturing, then data from all the machines and all the sensors on the machines, including visual feeds of cameras, etc., can be analyzed for optimization of the shop floor. So this is a use case where high speed, low latencies of the 5G network get utilized. We have smart care or telehealth, wherein again, remote monitoring of the patients and then transmitting the data either to the cloud or making it available in real time to the doctors can be enabled via this. We have smart energy and utilities. This is actually a very, very interesting use case wherein, for example, there are close to about 60 to 70 lakh transformers in India today. And even if we take the use case of monitoring these transformers, for example, is a very big use case in it. And transformers is just one example. It can be monitoring of, say, transmission lines. We have a couple of lakh kilometers of transmission line in the energy segment. Monitoring all of these transmission lines is a big, big challenge. It is a huge expense today. If certain devices can be enabled and monitored, that's a very big use case. These lines go through very inaccessible territories. Drones are being used to monitor these transmission lines. So it's also a cross-domain kind of use cases that get enabled by this. And we have smart city and education. We all know of this, so I'm not going to do a deep dive in the smart city. Surveillance, parking systems, uh, expected time of arrivals of city transport, making the city more efficient, water management, etc. use cases. And smart education, content dissemination in a much smarter way. Interactive education are some of the use cases for high speed, low latency communications using 5G network. So this is a very broad spectrum, kind of gives you, I would say, 100,000 feet level view of where the use cases are and how the 5G networks are. And I guess over the last 1.5 days, you would have done a deep dive on the characteristics of 5G networks, what properties it brings to the table, what properties can be used. So anyway, we are not going to get into the details of all of that. Now, specifically limiting myself to Art Park, we are looking at three use cases. And as Sheila had discussed in the opening session, and probably it was touched upon in the other sessions, the first use case we are talking about at Art Park out of this Center for Excellence in 5G Networks is about the drone corridor. So as we know, the proliferation of drone is going to grow, and uh, as the number of drones grow, there would be a need to regulate or monitor these drones, the way they fly, allocate them paths. It's just like the aviation industry. When you book a flight from point A to point B, there is a set path that gets allocated, the path gets monitored. But this can end up being a very, very high density kind of a use case, wherein you have several drones in the sky. We have to ensure there's no collision, we have to ensure the path of it, we have to ensure that there is location awareness of the drone. So these are all high bandwidth, very low latency kind of applications. How do we allocate? How do we geofence the drones? So on and so forth. So all these are being looked at as a part of the drone corridor experiment that we are trying to do at Art Park. Maybe we can have some other time a more detailed description of the drone corridor project that we are trying to do here. The other use case that we are trying to target at Art Park is the factory digital twin. So this is all about instrumenting a manufacturing plant or a factory floor with 5G networks and sensors, which and cameras and lidars, which are getting their data into the cloud or at the edge device, and then understanding this data or understanding the creating a context awareness of the entire situation on the floor of the factory. So this is more or less like creating a digital twin of the floor of the factory. And then when robots or autonomous vehicles move around the floor of the factory, there are several use cases that emerge out of it, like collision avoidance, geofencing. And then if we have a milk run going on the industry floor, maybe certain fleet management use cases that come about it. In addition to that, based on this data, we can look at how the entire end-to-end process gets optimized. So this is what we are going to do at scale in Art Park, wherein right now it would be a tabletop kind of an experiment, but eventually we will set up an entire test bed with a practical industry, and then we will look at enabling of various different use cases towards bringing in efficiencies on the shop floor. So these are the two use cases. And the third use case is where I'm going to go and do a deep dive, which is the mobility space. So the third use case we are talking about at Art Park, in which I'm going to do a slightly more deep dive into it in this presentation, is intelligent connected vehicles, right? So we all know that for some time now, at least for the last couple of years, there has been a lot of talk about automated vehicles. We have seen startups coming on, research papers along the lines of what is called as ADAS, right? So automated driver assistance system, and there are levels of ADAS, right? So your level 1 to level 5. At the lowest level, it is like simple assistance. You get certain alerts on seeing an object, or you get certain alerts on a lane departure. So if, for example, if you see the latest vehicles from the Toyotas, the Tatas and Mahindras of this world, on your dashboard of the car, whenever you are trying to overtake someone, you will get a lane departure warning if you have enabled it, right? So this is kind of an ADAS at level 2, where the user is informed of his intent and his action, right? And if we then take this to the extreme case, we can actually do automated braking, we can do collision avoidance. There are so many use cases that emerge. So in the four-wheeler segment, I would say the use cases, or a lot of ADAS use cases, have matured a lot. There have been OEMs which have been working on it for several years. Even in fact, we have Tesla, which is trying out autonomous driving. There are several other companies which are trying out autonomous driving. But most of these use cases, are driven by sensors on the vehicle. The analysis is on the edge itself, so you have some computational capability on the vehicle ECU or on the vehicle computer, if I may use that word very loosely. And then the decision is taken on the vehicle itself, right? There are certain use cases which are connected, but right now they are not very mature. So what we are going to talk about here is, if we are enabled to connect the vehicle to either the edge computing or to the cloud, or between the vehicles, if we can enable information exchange, what kind of use cases or what kind of problems we can solve. And that is where we are moving towards. That is, we are moving from a completely independent, unconnected decision making system to a connected, distributed, federated decision making systems, which can collaborate with each other. And that is where the world is moving towards, and that is exactly what 5G is going to enable in this case. So one of the themes that gets enabled here is what is called vehicle assistance and vehicle safety, and we are trying to do a deep dive in it in the 5G context, right? So uh, a brief history of how this all started, right? It all started with release 14 of the 3GPP, which kind of provided the CV2X interfaces. It had a PC5 interface with an RSU on the road, and then it enabled a V2I and vehicle to vehicle and a vehicle to person communication without actually going into the cellular network, right? So this was kind of a technology where you had an RSU, a roadside unit. The roadside unit acted as an intermediary to enable a communication between two vehicles, or to a person, or to an infrastructure. And this kick-started in the early stages of 2017, wherein certain use cases that were related to, let us say, if the vehicle comes in close proximity of each other, there was an automatic braking, or there was an automated slowdown of the vehicle, or when a pedestrian was crossing a road, the pedestrian was alerted in some way, or the beeper used to go off. So there have been several projects, and in fact, some of these technologies have matured to be inside at least the high-end vehicles that get enabled by some of these services. And then the other part of it was the vehicle to network service with the UU interfaces that got enabled, so the vehicle could communicate with the cloud, and the cloud then to do some computations, especially uh, the infotainment system on it. So mapping services, the fidelity of the mapping services really improved with these UU interfaces and the cloud services that got enabled with this interface. And then over the period of time, we are now at release 17, 18. Each of these releases are maturing, and a new set of use cases are getting enabled, right? So if we look at release 17, the reduced capability devices is something that we are talking about. We are talking about of non-terrestrial networks, so on and so forth. And I'm going to talk of some of these use cases that the later releases of 5G network and the characteristics that they bring along with them are capable of enabling. So What we are going to do is, categorize the use cases into some very simple categories, and then see what are the requirements, what are the challenges that these use cases bring to the table, and then discuss probably, the potential reference frameworks that can help implement some of this as we go along. So now let's look at a vehicle. Maybe I will stop here if there are any questions. I'm not sure. I didn't look at if anyone has something to ask. Okay, I'll continue then. Uh, so let's look at the car and the two-wheeler. So at a very, very broad level, we have, if we look at the road segment as such, or mobility segment on the road, we have an infrastructure where there are traffic signals. We have cameras at intersection of the traffic signal, and these are all networked today. We might have also dedicated infrastructure-based cameras, not necessarily at the traffic signal. They might be for monitoring purposes or deliberately installed for V2I communication. Especially, there are certain use cases of, say, parking slot detection, etc., which require certain visual sensing. Apart from a parking sensor, of course, parking sensor is one of the ways of doing it, but not necessarily the only way of doing it. Then we have the vehicle. The vehicle today is also equipped with a lot of sensors, right? So we have a radar on the vehicle. So in fact, some of the high-end cars, so having a front radar on and a back radar is very common. So for those who are new to this terminology of radar and lidar, uh, uh, when you drive your car, you put it into reverse, you're able to see the back image of it, and if you're close to an object, it gives a beep beep sound, right? So that is because the radar is giving a warning of proximity on the car. The radar or lidar depends upon the implementation from various vehicles. So we have the radar, the lidar. We have cameras on the car. We have certain ultrasonics on the car. We have tire sensing. Nowadays, we also have side sensors onto the car. Of course, we have location indication in terms of GPS. We have accelerometers on the car. We have vibration sensors on the car. So it is truly, completely the most sensed asset today in the world. Now, where it is getting evolved is right now the data that comes out from all of these sensors today is consumed by the car itself. Okay, for example, the application just that I described of a beep coming out when you are reversing the car, or when you are in close proximity of another object, there is a beep that comes in. So the data that comes from many of these sensors is actually just internally consumed by the vehicle. It is neither communicated to other vehicles nor is it communicated to the cloud, because until now there was no infrastructure available to communicate this information at scale, at that speed, and at that latencies, right? And this is exactly what 5G is going to enable. So now imagine all of this data that a car has from the various sensors that it is equipped with. If we are able to package all of this data and somehow figure out a way to communicate this data to the cloud to enable certain intelligent decision making, or communicate this data to another vehicle in its close proximity. How do we communicate? When do we communicate? Is probably where the reference framework comes in. A lot of different use cases can be enabled, right? So that is exactly where we are heading to right now. And that is exactly what a 5G network will enable. Now, what is the ADAS equivalent on a two-wheeler? We talked about the four-wheeler, and four-wheelers are very similar. Even trucks have similar capabilities, buses have similar capabilities. So four-wheelers more or less are ADAS capable. What about two-wheelers? So the ADAS equivalent in two-wheelers is also referred to as advanced rider assistance system, right? So this is something which is work in progress, I would say. Uh, it's a Not many things are today available. Some things are available which can fall under the category of advanced rider assistance, but for example, the one of the features which many of the bikes today have is what is called a tilt angle. That is available, but beyond that tilt angle, at least very few features related to ADAS are available. So we are going to look at few use cases what ADAS can have potentially. It's an open area, it's a greenfield area according to me. uh, for those who want to do a research or those who want to get into entrepreneurship, so there's a vast scope that can be done as a part of ADAS. Having talked about the vehicle and its relation to the infrastructure, so the vehicle is equipped with sensors, the infrastructure is equipped with certain sensing, that is basically cameras. We can also have radars, we can also have certain positioning systems equipped in the infrastructure, and if we can aggregate all this data, then a set of use cases emerge that 5G can enable. And the next 4 or 5 slides, we are going to talk about that these use cases or these categories of use cases. They're not specific use cases, right? So the first among them is called as cooperative maneuvering, right? So this is a class of use case, and lane merger today is one of the use cases in cooperative maneuvering. But this use case is sharing the local awareness, and you might have come across these situations when you are driving your vehicle, either be it a two-wheeler or four-wheeler. When you're joining an intersection on a highway, you are at a blind spot. You do not know what vehicle is merging onto the lane that you are going to go into an highway, right? So creating that local awareness that there is a vehicle that is coming. Let us say I'm driving on this bylane that you see on this figure, and I get a notification from the network or from a cloud service or something like that, that there is a vehicle coming at 100 kmph. You will have to slow down to 30 kmph. Otherwise, there's a possibility of a crash. I mean, okay, I'm describing it verbally, but some way of communication, right? That there is going to be a possibility of an impact or a crash if you continue driving this fast, right? So in general, what cooperative maneuvering is about is making, if we uh, take a context. So context is, let us say, a circle with 50 meters as a radius, and we make every vehicle aware in that 50 or the 100-meter radius of, say, the relative position of every vehicle, the intent of every vehicle. So that is what is called as local awareness. And what are the driving intentions, right? So the driving intentions are easy. Speed is one indication of a driving intention, braking is another driving intention, acceleration is a driving intention, right? So if we are able to make the vehicles in this vicinity aware of these driving intentions, then the others can take appropriate actions, either manually, or there can be an automation algorithm also possible of, say, auto braking or slowing down, or accelerating to join fast, whichever way it is possible. So this is what cooperative maneuvering is about, right? Now, if we look at the technology challenges, if we were to solve this problem, right? So uh, some of the challenges I have listed, I mean, there are several of them. So the most important part of them, or probably that come top in the agenda list, which uh, impact developing a solution for this. So common interpretation of driving intentions, right? So what is a common interpretation? in the sense that look at it this way. So I am driving at 100 kilometers per hour. The other person is driving at 120 kmph. So for a person driving at 100 kmph, a person at 140 is accelerating. But if there's another person driving at 200 kmph, the person at 140 is actually decelerating, right? So it depends on not only on decelerating in the sense he is coming slower or the merger distance is higher, etc., etc. So not exactly decelerating. So the interpretation between the vehicles within a given region is not the same. It is different for different vehicles depending upon your own context, right? And given this data at that speed and at that computation level, are we able to determine a personalized interpretation of everyone's driving intention, right? So this is one of the challenges in this data aggregation or data fusion. Then comes in joint optimization trajectories, that based, assuming we solve the problem of interpretation of intentions, we come to know that, hey, he is going to accelerate, he is going to brake, he is going to decelerate, etc., etc. Now in the mix of all this situational awareness, how do you see the final scenario? Who is going to collide with him? Who is going to move in whose direction? Collision is the last case, of course, but can we then derive a general trajectory of what is going to happen in the next 1 second, 2 seconds, 5 seconds? Typically, in the automotive world, when we are talking about cooperative maneuvering, we don't go beyond 10 seconds. So, what is going to happen within the next 10 seconds? Can we build a picture of that? How do you represent that picture? How do you communicate that picture? Is that decision taken centrally or is that a federated decision? So, these are all questions today which are work in progress at every stage, right? Then acknowledgement of maneuvering plans. So, assume that, you know, we somehow make these trajectories or we somehow make these so-called actions or plans, and we manage to have some schema by which we communicate these plans to every vehicle in the vicinity. You have to ensure that someone sticks to this plan, right? So I don't know if you are, if you are follow, some of you might be following the avionics. So the avionics has something called as a TCAS, which is a collision avoidance system, right, on an aircraft. So in a collision avoidance system, the proximity of the aircraft to the aircraft is measured and communicated to all the aircrafts in the vicinity. And the pilots have to acknowledge. So it goes with an action also that, you know, if you are in close proximity, one of the planes would be asked to go up, the other would be asked to go down so that the separation is at same levels, right? But the pilot has to acknowledge to a TCAS message mandatorily saying that I am going up, and the other pilot has to acknowledge I am going down, because if they take opposite actions, then it is also a collision, right? So there is an acknowledgement process there. Now, in this, what is an equivalent of that acknowledgement process in the automotive world? Nothing exists today, right? Do we even have the time to acknowledge such a thing? Because the events in the automotive world might be very fast. You may not even have the reaction time to do it, right? So, are these acknowledgements with a manual intervention? Should they be automated? Should they be action oriented? So, these are fairly open things. So, right now, even at an L5 level of the vehicle, only autonomous driving vehicles have acknowledged manual plans. Any level below level 5 today does not have an acknowledged manual plans. So that's again an open area. Then what's the authenticity of shared information and timely communication? So these are some of the challenges. I might want to hack into this and feed the network with the wrong data set so that the crashes deliberately occur, right? So uh, this is so these are some of the challenges in cooperative maneuvering. Let's come to cooperative perception. Cooperative perception is uh, ability to extend the local perception beyond the line of sight. I mean, a very common example, when we have a truck in front of us and we are trying to overtake, we are unsure whether there is space in front of the truck where after overtaking I can get it, right? So I still do not have that information with me, and there are several such situations. Several use cases emerge out of a cooperative perception. So is it possible for me to create the image of what is available in front of the vehicle in my map? Right? Today maps, they tell me only where I am. They don't tell me where others are. Right? But if I look at a 5G network, if assume all vehicles are connected, this information of relative location is available to the network. Right? What is the relative position of the vehicle? Now, if this information can be made available in the map, I think that's a fantastic value add, right? So that is exactly what the cooperative perception is. And if this information can be augmented with the sensed data of the vehicle, even better, I get more accurate information, right? So this is all about cooperative perception. Some of the challenges that are involved here are multi-vehicle sensor fusions. There's a sensor data from different vehicles. We will have to merge all those sensing information. We will have to merge all the network information from it in order to derive a common picture. Map merging is a very tricky topic, or topic of research right now, that uh, the different vehicles might be logged on to different mapping services at different accuracies, right? They may not be with the same network provider in a 5G world also. And different network providers or different satellite networks that use the GPS, assuming we use GPS for location, might have different interpretation of the given location. And the closer we get, the resolutions are different. Then how do we create a common reference out of this various informations, or various temporal and spatial information? That's the challenge. Different vehicles might have different sensors calibrated with different precision, accuracies, etc. Each sensor will have its own drift. How do we compensate for that in our data fusion algorithms is another area. Uh, Time synchronization. Not necessarily every vehicle is on the. So look at it. You have a visual reference, but look at it as a system. As a system, the clocks of each of the vehicles that are participating in a cooperative perception algorithm need not be time synchronized. They might be talking to different time servers. The time servers might have a drift among themselves, or the satellites that they use for time syncs might be different. So how do we do this time synchronization? And of course, the last but not the least is, how do we communicate this? Should we show it on a map which the user is using? Rather than showing a single vehicle on a road, shall we show the relative positions of all vehicles on the road? So today Google does this by just showing a red line, or let us say a green line or a blue line, saying there's no traffic, right? So it is doing some sort of a user experience, or it is doing some cooperative perception in terms of aggregated traffic density. But that aggregated traffic density is not sufficient to take vehicle safety decisions. It just doesn't have the fidelity of doing a vehicle safety decision. So that is exactly what user experience will be. That how do we enhance the mapping service, or is there some other way by which we will communicate to the user on this, right? So this is cooperative perception. The other class is cooperative safety. Cooperative safety is more about pedestrian safety, or VRUs, vulnerable road users, who do not have any sensing on themselves and have to rely on infrastructure sensing. So let us say you're standing on a road, or you are trying to cross a road, and there is a speeding vehicle comes at, there is all the probability that it will crash into you. how can we enable such a use case where both the vehicle and the user are alerted about an impediment or are alerted about a possibility of a collision, right? So this is what is cooperate. This is again just one of the use cases. This can be extended to multiple use cases in a vehicle safety context of vehicle to vehicle crash, vehicle to pedestrian crashes, speed control limits on vehicles in the presence of objects, road blockages, so on and so forth, right? So that is what is cooperative safety. Some of the challenges in it is, a reliable detection of VRUs, vulnerable road users. So road users themselves probably in today's world have cell phone, right? Cell phone data, and relative positions can be acquired via the cell phone data if they're connected to the same 5G network. But beyond that, we have to rely on infrastructure sensing. Based on infrastructure sensing and the network data, how can we do proximity estimations, right? Uh, vehicle to vehicle communication is relatively easy because they might be logged on to the same RSU and we might be able to figure out a way. But how do you do a communication with an VRU? So I am seeing a person, and somehow if I have built some algorithm saying I'm able to detect a potential crash, I should be able to inform the user, right? Maybe as an alert or maybe as, and the user, it should be in a way which is non-distractive, right? So how do we communicate with the with the VRU? So that's a big area of research actually. Then a common frame of reference between infrastructure and vehicle sensing. The same picture should be created uh, based on the data acquired from the infrastructure and the data that the vehicle generates. How do we overlay both the data? This is not only a sensor fusion problem, but this is also a frame of reference problem, that both of them should be generating the same frame of reference or have the same view of the context and the situation, right? So occlusions, how do we address that? Intent, how do we address that? Become a part of this cooperative safety. Of course, we can bring it down to very constrained problem definitions and try to solve it one by one, but that's a topic of another discussion probably. And last but not the least, communicable identity of the VRU. So communication to the VRU is one part of the story, which is more about user experience, how to communicate. But how do you detect which user I should communicate to, right? Does the would you rely on the infrastructure to communicate? Would it be an intent-based communication that maybe the user that is closest to the asset where there is a higher risk, you decide to communicate first? How do you decide? How do you get the mobile identity of the user under a GDPR rule, for example, where it's not very easy to get access to identities, right? So these are certain areas of cooperative safety that need to be looked at. Autonomous navigations, we all know of this, but because there is a lot of talk about autonomous vehicles driving on roads, there are so many startups that are getting into this, so on and so forth. Here it is not only about not autonomous navigation, but it is also about augmenting the available information with hyperlocal real-time information, right? So uh, what is hyperlocal real-time information? Every car, as we saw earlier, has a lidar and a radar. So they are actually sensing the information in and around them. And as I said, they are consuming the information for themselves. But if this information is made available to the external world, we can do much more. For example, if there is a blockage on the road, or if there is a lidar, for example, I can get a very accurate picture of the road condition, right? That there is a ditch here, there is a water collection here, there is a road diversion here, which is not available in real time in a mapping service. Google has started this to a certain extent, but that is with user intervention. Nowadays, you would see you will get an alert. There is an object on the road. Do you confirm yes or no? Right? on your mapping service you will find this, but that is just with manual intervention. So someone reports something and Google then asks for people that will you confirm this, and then if maybe there's an algorithm which says if 10 people confirm, maybe I will say that there's a road on the object. It is not automatic as of now, right? But this is exactly what a 5G network will enable. uh, if we aggregate or start using the car itself or the vehicle itself as a sensor, it is so rich in sensing information, right? So there was a project from TCS, if I'm not wrong, wherein they used the radar and the lidar in the car as sensors to detect empty parking spots. It was a very nice pilot they did where, when I'm traveling along the road, this senses empty parking spots on pre-located areas and reports that to the cloud saying, hey, look, this is an empty parking slot. So that was a very simplistic use case, but 5G can really enable very complicated or real hyperlocal information that can enhance the map and provide me with much detailed navigation or suggestions on selecting the right route, right? So this is what is autonomous navigation. uh, some of the challenges, how do I update the maps in real time with my sensed information? How do I ensure the authentication of my sensed information? What is my navigation strategy? How do I change my route in real time based on that? And then the main challenge is working with heterogeneous maps. So this is more about standardizing the map representation. So today there is a layered representation in a KML format, or there's a bunch of formats today available. Is that format semantically, it is syntactically rich, but is it semantically rich enough to accommodate such hyperlocal real-time informations, right? It's still a debate going on around that, and we need to look at that, and then based on that, how do we do the navigation computation or distributed routes, so on and so forth. So these are some of the challenges in autonomous navigation systems. And last but not the least of the use cases is remote driving. So, a valetless, say, parking is the simplest of use case I can think of. So the valet is at a remote location. You give him the car keys and he drives it. Your infrastructure is equipped with cameras. Your car is equipped with cameras. So it is like sitting in a call center and driving your vehicle, right? So while this may not be a very lucrative use case in an on-the-road scenario because we have autonomous driving vehicles, but off-road applications are tremendous, right? So we do not get, let us say you have an agriculture tractor and I convert that tractor into an autonomous or a remotely drivable vehicle. I can sit in a call center and I can drive the tractor sitting in a call center and plow the field. I need not employ a person to go there, which appears to be the biggest challenge today in the Indian scenarios, right? So there are certain set of use cases that come about from a remote driving perspective. Now, some of the challenges is safety, navigation in the presence of objects, especially humans. How do you avoid that? Real-time control of information. So far, we talked about information coming from the vehicle. So the let me say the uplink was a high bandwidth requirement, downlink was a low bandwidth, low latency requirement. But in this case, the downlink is probably a relatively high bandwidth and an extremely low latency requirement. Because if I sit, let us say, in my home with a steering column or the steering simulator driving a remote vehicle, the slightest touch on the accelerator pedal or my brake pedal should immediately reflect on my vehicle, right? So how do I establish that real-time control information gets communicated at that quality of service is something that is a topic here. Then what if my network fails? Right, we have to address that condition as well. Networks, though very reliable, we claim there is always a possibility that the network might fail, especially in Indian conditions. Then the vehicle should have a decision making capability on its own. So that is, how does it make decisions at the edge if the network connectivity is lost, right? Then we have security. Again, security is about data corruption, about someone doing a cyber attack on the entire system, so on and so forth. So that is another area that is to be looked at. And cooperative movements. If just like we talked about cooperative maneuvering, there you have the driver on the vehicle, right? But here, let us say you have two vehicles within the same vicinity, but two drivers are remotely driving it, right? Then this opens up a Pandora's box. Not only the vehicles should be safe, but the same information of what the vehicles are seeing should be communicated back to the driver, so that appropriate, so driver in the sense the user who is remotely controlling the vehicle should be able to see the same scenario. So there are certain challenges in that. So cooperative movement in case of multiple operators becomes a challenge. So broadly speaking, in an ADAS system, or when we talk about enablers of 5G, these are predominantly the five categories under which most of the use cases can be mapped, right? So uh, uh, and the challenges more or less are what I discussed at a very high level. I mean, of course, deep down there are several details which probably we can take up at some other point in time. In the interest of time, I will go over the rest a bit fast. Now, given that we have to do implement such a use case, if we have to do an uh, requirement derivation, this is just one example of a requirement. So you will have automotive requirements, you will have network requirements, and you will have some qualitative requirements. There will be, of course, a lot of other detailed requirements. It's not so simple that we stop at this, but this more or less conveys the gist, right? So we will have to, when analyzing a use case, we will have to look at the automotive requirement, especially, what is the localization I need, or what is the accuracy of my sensing is what localization means in this context. uh, to what is the minimum distance, minimum car distance I should get recognized that there is an object in front of me based on the algorithm. At what speed am I driving, and what should be the accuracy of the speed recognition that I should have. So these are some of the automotive requirements. We will have certain network requirements in terms of communication rate, data rates, latency, reliability, etc., etc. And then the cost and power consumption, of course, and the security part of it, right? So whenever we are doing our requirement engineering for this use case, in trying to identify what kind of sensors I should select, or what kind of network requirements I should have, or what kind of software that I'm going to do, these are certain exemplary ways for this. Now, the rest of the things I'm going to talk a bit about ADAS. So just to set the context, this slide is taken from Ministry of Road Transport. As you can see, 60% of the vehicles involved in a road accident are two-wheelers, right? One of the vehicle is a two-wheeler, or the pedestrian, right? It's an enormous number. So pedestrians, bicycles, and two-wheelers together form almost 60 to 65% of the road accidents, especially fatalities, and 80% of the fatalities are in this category, of all the fatalities. And then if you look at where the accidents occur, most of the accidents are occurring around a junction where there is a blind spot, or you're not able to see the other vehicle, or you're unable to judge the speed, so on and so forth, right? So there is definitely a need to build something like an advanced rider assistance system in this. Now, what are the use cases that emerge out of this? So I've listed some top few. There are definitely several others. Again, as I said, this is just to kickstart your thought process around this. Tilt detection. So whenever I'm taking a turn, my bike tilts. Can I use my accelerometer to detect by what angle I'm going to tilt? And if I can detect the angle by which I'm going to tilt, I would be able to control my speed better, or I might auto select a speed in my vehicle ECU such that it doesn't allow me to go beyond a certain speed. So there is an immobilization. If tilt detection can be linked to vehicle immobilization, that's the use case that emerges here, right? The other is e-call. So whenever there is a crash or the fall detected, uh, can we auto initiate an emergency response? That is, if the vehicle is a connected vehicle, means it has the capability of sending an SMS or making a call. Why doesn't the vehicle, if it gets crashed, and assuming that the telematics device is not destroyed, it makes a call? But more than that, can the infrastructure initiate it even if the vehicle is destroyed? Right? The infrastructure knows there is a crash. The infrastructure also knows the identity based on probably the eSIM or whatever goes into the vehicle as a communication identity. So e-call systems today are vehicle oriented. Can they be infrastructure oriented? Right? So that is the use case here. Then airbags as apparels. So on a two-wheeler, I mean, today they are very expensive. You get a jacket which is an airbag. So when the vehicle detects a crash, there is a Bluetooth communication between the jacket and the vehicle, that on a crash, when you fall down, maybe the jacket has a sensor. I'm not too sure. Yes, I do know that when you ask this jacket with some of the high-end bikes like BMW and all, it also has a sensor. When if detected, it is inflated, right? But can we do this in a more economical way for the developing nations like India? What kind of safety measures can we do? Apparel airbags is probably one of a very, very new area that needs to be looked at. Smart helmets. Today, helmet, I mean, we just have a helmet because the rule says we have a helmet, but they're pretty much, I think, of no use because of the various considerations. But can we make them smart? I mean, we do get helmets with probably, a speaker and a headphone in it. But that's not what is smart. Can we have an HUD, a heads up display inside the helmet visor? Well, what you see on the bike's display or the HMI gets displayed inside the helmet, right? And with EVs, battery safety, thermal runaways, can we get early warnings, diagnostics and prognostics, and the heating element of the battery? Can early responses, or can early things be done with this? And then pay as you drive is an insurance use case. So you incentivize payment based on how you are driving or the driver's parameters. This is a topic in itself. Probably sometime we can get into the details. So these are some of the use cases in the ADAS. I'll take 5 more minutes. Some of the cases we talked about is accident and crash detection. So parking violation and parking circulation time. This is a very interesting use case. There is a statistics which was carried out by one of the organizations. If I was not wrong, it is the London Transportation System, on how much fuel is wasted in searching for parking lots. And I think the number is something like a couple of billions per year, globally. I'm saying, not India specific, right? Huge number just searching for parking. So this is called as parking circulation. That is, you are inside a parking lot. So and inside the parking lot, you are just going either up and down if it is a working parking lot. If it is an open parking lot, you are just circulating around searching for the parking space. And this is a huge fuel loss, carbon credits, etc., etc. So can we use sensing technology or even 5G to actually direct a user directly to an available parking space, right? Parking slot rather, not space. Then comes in hazard notification of any object on the road. It's a very low hanging fruit, probably can be looked at. The other two use cases are theft detection and towing detection, they are very relevant in an Indian context. How many times you have faced that your two-wheeler has been towed away by a police because you parked it wrongly, and then you don't know where it is parked, where the police have taken it. So you spend a lot of time with that. So can we have a towing detection enabled on the vehicle, which is an AI ML plus an infrastructure sensing kind of a thing, and then based on that you know where the destination of the vehicle is, and you are alerted that your vehicle is being towed away, and so many use cases emerge out of that, right? Okay, having talked about this very quickly, the conceptual framework, we will have sensors, we will have some kind of an acquisition which is about information collection, we will have some kind of an edge computing unit. In the edge computing unit, we will have some AI ML algorithms running, which can be run on the vehicle, which can be run on the infrastructure, but which can also be on the cloud itself. Then we will have certain cloud computing services, and this is a federated model. Based on this federated model, we can then arrive at certain conclusions, and the messages then can be or the control outputs, all the alerts, all the events can then be communicated to the end user, right? So this is more of a conceptual framework that we are talking about here. Then there are certain data challenges that go in. The data challenges, is we are asking for data from the vehicle, we are asking for data from the infrastructure. So there has to be some data ownerships. People have to be incentivized to share that data. There has to be a framework where people are given the choice that which data they want to share, which data they do not want to share. We have to come out with interoperable data formats. We have to come out with some audit trails for the data, so that if there is a monetization possibility, that can be explored along with it. So all of this come as a part of setting up this data framework in a 5G network, which today it is assumed that users will share the data. I'm not too sure if this assumption will stand for very long, considering that GDPR and even India, we now have a data sharing policy. Uh, so right at from a design phase, we should be aware that data doesn't come for free. And then if data doesn't come for free, then what are the enablers we should build, so that we enable, at least at an architectural level or the framework level, that if the right policies come in, then we are in a position to uh, accommodate that, right? So that is all about the data challenges that need to be addressed. Broad level framework, there would be certain triggers. There would be a strategy deviation from the trigger. So proximity or object detection can trigger something. Then I have to devise a strategy from it. Based on the strategies, we will have to derive certain gain function. If I do this, what is my gain or loss? If I do that, what is my gain or loss? Based on that, certain outcomes, and based on that, certain alerts, notifications, or controls can be enabled, right? So this would be the high level flow of any framework or any ecosystem that we try to build, or any algorithm we try to build at a very high level. And then we will have a physical layer. I'm not going to get into the details of this, because this is it's going to take some time to run through this, but in principle, we have physical layer where infrastructure and vehicles provide me with the sensing information. We have a fog computing layer, then we have a multi-access edge where I can run my edge algorithms, and we have a cloud computing layer where another layer of computations and AI ML or learnings, reinforcement learnings, or any other type of learnings can happen, and the model gets pushed down into the network. The idea being, keep your decision making as close to the edge as possible, but offline do the computations on the cloud. That should be the philosophy that drives this reference framework, right? Now, if I come to a common interface, if the thought process that we are also looking at or driving out of Art Park is, Can we build a digital public interface for this vehicle safety? Even if my vehicle, if I agree to share certain data comes from the infrastructure. Vehicle safety should be something as simple as the unified payment interface, right? Someone should be able to consume the APIs and build intelligent applications and offer it as a service. So, can we create such a digital public infrastructure? It is still a topic of research. It's a thought process right now, but that is the thought process. And if we have to go in that direction of thought process, we will have to build certain common services. Can we split down the 5 or 6 categories of use cases into certain common services? For example, object detection, path computations, platooning, network selection, traffic monitoring, etc., etc. These are all common services which can then be combined or orchestrated at an application level in order to build a rich experience. So, incident detections or cooperative navigation, what I talked about. So if we take an example of collision warning, right? Collision warning is a combination of an object detection, a path computation, and a sensor fusion, for example, right? If you orchestrate these services right, you can in principle build a collision warning system. So that is where we are heading to, or we are trying to look at if we can build a digital public infrastructure in this direction of vehicle safety. I'll stop here. Sorry, I ran 5 minutes more than the time allocated, but I'll be happy to take questions if any.